Can you hear me? Hello, yeah, for coming. Just a request, like if you can have like the guys at the back to come over, closer to the front. We appreciate that. So we can see you better and you can see the presentation. Kasi our speaker here will be drawing something on the whiteboard, so it would be easier for you to see them as well. Thank you.
This what? Okay.
Yes. Perfect. Okay. No problem. Sige. Sorry. And on a timer. All right. So again, good morning, everyone. Good morning. Again, I'm Sherwin Almazan, and I'm from ADI, Analog Devices. And again, I would like to thank everyone for coming over today, for giving the whole day for time today to witness this seminar. So before I turn you over to our speaker, let me just briefly introduce you to him. I have some quick facts about him. So our speaker is Mike Engelhardt. He's also from Analog Devices, and he's the director of the simulation development at ADI. So Mike has been writing physical simulators since 1975, okay? And his first simulators were written for high-energy physical labs and instrumentation companies working in charged particle optics and oil exploration. He created LD Spice and leads its development and the model generation. And LD Spice is Mike's third electronic circuit simulator, and is based in the collection of the original numerical methods that he invented. So without further ado, I turn over to Mike Engelhardt.
Thank you very much, Sherwin. Very much appreciated. All right. Magandang Maga. So, like he said, I've been writing physical can you guys hear me? Okay, good. Raise your hand if you can't hear me. All right, good. I've been writing physical simulators since 1975, and the one thing that I have learned in these decades of writing simulators is that the best simulators are not from software companies. They are, without exception, developed by the company that needs to use that type of simulator. And I have a few examples here to show the normal pattern. Say you want a charged particle optics simulator. That's a piece of software that will tell you how electrodes and electromagnets would focus a particle beam traveling through a vacuum. It's the sort of software you use for designing a cathode ray tube or a particle accelerator or a scanning electron microscope. Now, if you need a piece of software like that, you have choices. Basically, you're numerically integrating F equals ma, which is the example that we learn in calculus university courses for numerical integration. And people write this to try it out because it's kind of fun to write something that integrates F equals ma. So there's free charged particle optic simulators. There's a few of them. Now you can buy, there's also charged particle optic simulators for sale. You can spend up to $100,000 for a license to a charged particle optic simulator. But if you want the very best charged particle optic simulator, it is not for sale. It was developed in-house at a scanning electron microscope company, and that company invested in their own infrastructure to develop this simulator so that they wrote that simulator explicitly to be a better simulator than you could buy from anyone at any price. And they wrote it so that they could design better microscopes than their competitors. That's the business model under which all the best simulators are developed. Here's another example. Say you want something called a high-speed MOSFET solver. That is a circuit simulator that will give you the electrical waveforms of an integrated circuit that consists of millions or even billions of MOSFETs. There's software that does that. You can buy software that does that. You can spend up to $1 million for a single-seat license to a high-speed MOSFET solver. But if you want the very best high-speed MOSFET solver, it is not for sale. It was developed in-house at Intel, and they developed that simulator explicitly to be a better simulator than you could buy from anyone at any price. And they wrote it so that they could design better microprocessors than their competitors. That is, in fact, one of the key strategic differences between Intel and AMD. Intel develops their own simulation and CAD tools, and AMD buys them. And the consequences of that strategic decision played out at one point in the marketplace where there was a while there, a couple of years ago, where many people had forgotten you could actually buy an AMD microprocessor. I mean, they just lost the market. The only reason why they're coming back into some attention today is because Intel feels they've so conquered the market, they feel they have better things to do with all that money than make microprocessors. That's the only reason, not because AMD won with their method. Okay, now here's another example that really underscores the mechanism of the business model that I'm talking about. Say you want a simulator that will compute the radar return from a warplane. You can buy software that will do that. There are high-frequency finite element, three-dimensional finite element solvers that you can use to develop your intuition and how radar is reflected off of different shaped structures. But if you want the very best simulator for computing the radar return from a warplane, well, it's not for sale. The people that wrote that simulator didn't write it so that they could collect some licensing fees off of its use. They wrote it so they could design those planes and sell them. They were interested in selling the planes, not the simulator. And that is the business model under which I developed LT-SPICE. 20 years ago, I had already been writing simulators for about 25 years. And it occurred to me that there were numerical methods that were not used in SPICE programs. And SPICE was always something of interest because I think maybe SPICE is the simulator that's impacted mankind more than any other simulator. I think that's a very fair statement to say. I thought, well, you could write a better SPICE program. I could write something that would be faster, more accurate, and more numerically robust. That was the juncture of my life I was in 25 years ago. Well, what do I do with that information? Should I start a company and try to, collect licensing fees with this? Well, I already knew that was the worst possible way of developing a piece of a simulator. I already knew that was that was not useful. So that is when I joined my neighborhood semiconductor manufacturer. I lived within a couple of miles of a company called Linear Technology Corporation. That was my path into analog devices. I worked for Linear Technology Corporation, and for the last couple of years, we're probably part of Analog Devices. So I work for Analog Devices. But I wrote LT-SPICE for in-house IC design. I wrote that simulator explicitly to be faster, more accurate, and more numerically robust than any SPICE program at any price. That is why I wrote the software, and I wrote it so that my neighborhood semiconductor manufacturer could design better integrated circuits, better analog circuits of our product class than other companies. That is why I wrote the software. Okay, now what's unusual about LT SPICE is that we also give it away. We let you have exactly the same simulator that we use in-house for IC design. And when you download it, you go to the same website, you spin the same disk, and you get the same file as our in-house IC designers. And that program is not crippled in any way. It's unlimited circuit size, unlimited content. You can use third-party. You can simulate circuits of no commercial interest to analog devices, and it even mentions so in the license file. If you have a lawyer read your health file, says, "Oh, but yeah, you can use this for using all third-party models from other companies," and that's all okay. So what the let me be clear what's up here. Analog devices does not give LT SPICE away out of a charitable interest in the well-being of mankind. Okay. We give it away because it is in our interest to do so. It is in our interest that you have a really good analog circuit simulator so you can design circuits using our parts, and you can simulate them faster and you will buy them faster. That we have a vested interest in you doing that, and there's no downside to letting you use this good simulator. The license says you can't use it for designing integrated circuits and then go to some fabless semiconductor manufacturer and compete against us. So there's no downside to it, but we give it away out of our selfish interest, if you will. Now, so what LT SPICE has done, the situation that LT SPICE has presented to the market is this. You can buy a SPICE program, or you can get one for free. But the one you get for free, well, it's faster, it's more accurate, it's more numerically robust. This is an important decision as to which SPICE program you're going to use, so you need to get it straight. You can get a free SPICE program, or you can buy one. But if you buy it, well, it's not as fast, it's not as accurate, it's not as numerically robust. Now, if you give engineers about a decade to think about it, they will use the free one that's faster, more accurate, more numerically robust. LT SPICE is overwhelmingly the most widely distributed and used SPICE program today. It is used approximately 1,000 times more than all the other SPICE programs combined. It's downloaded, I haven't looked at numbers recently, it's downloaded between 1 and 4 times per minute. And that means that in any 24-hour period, Analog Devices distributes more licenses to LT SPICE than, say, Cadence does a P-SPICE in 10 years. And we do that every single day. All right. Now, what this means is, basically, LT SPICE is the industry de facto SPICE program, has been for many, many, many years. It's really come to a point where if you are doing analog circuit design, but you are not using LT SPICE, then you would have to make up an excuse to justify that behavior. All right, good. Now, I know that's a very strong statement to say about a piece of software. Here's the deal. It just bugs me that there are people that think that LT SPICE is not as good as the SPICE simulation software that you pay for, when it is in fact the opposite that is the truth. Okay? I mean, I have in fact committed my life, my metabolism, my body, and my health to writing this kind of software. And other companies that sell this stuff don't have anybody like that. And I just want to get this off my chest, and I'm done now. Okay, so here's the deal. I'm going to talk all day about LT SPICE, and you can ask me questions at any time. You can interrupt me with questions. Interrupting with questions has two good purposes. One is that it's a little break for me, because for me to stand here and monotribe for hours and hours is intellectually fatiguing. You understand that. And the other thing is that since I am a native English speaker, and you may or may not be native English speakers, it lets me know I'm speaking accurately and clearly enough that you're understanding. So it gives me feedback, which will be very useful. So you can literally jump up out of your chair, raise your hand, and say, "But I think this," and what's your? That's all good stuff. That's all good. From the remote sites, also, you're welcome over there. We've discussed this. You guys remotely can also ask me questions. Okay. So now. Inside Analog Devices, we're always improving the numerical methods used in LT-SPICE. We're always thinking of new ways of doing the same thing faster. We're always making little improvements to it. But the thing that's most obvious, the most obvious changes as you see to LT-SPICE is that the GUI changes. And the most recent change in LT-SPICE for the GUI has been when we've moved from LT-SPICE 4 to LT-SPICE 17. Okay? LT-SPICE 17 is the current version. LT-SPICE 4 is actually no longer supported. You can't, it's built with a very old compiler you can no longer install on a modern computer. So you have to use LT-SPICE 17. There's no support route for 4 anymore. All right, now the biggest difference visually from LT-SPICE 17 to 4 is that it is native multi-monitor, meaning you can unlock a schematic or waveform window from the main application frame and then move it out of that, put it on a different monitor and maximize it there. So it's native multi-monitor, that's one thing. It's 64-bit. The 64-bit is useful for the waveform viewer. It actually doesn't take very much memory to simulate a circuit. 32 bits is enough for huge circuits, that's not a problem. But to look at the data that comes out of these things, they just generate horrific amounts of data. And even LT-SPICE 4, which is a 32-bit app, would implement its own 64-bit address space on the disk and just page in memory. It could only address 3 gigs of internal memory on your machine. Now, if you have 16 or 32 gigabytes in your machine, it can use all of that to page in waveform data. So it's a flat 64-bit address space. And it's Unicode, which I don't think interests you very much, but what that means is you can have any character of any living language. You know, traditional Chinese, simplified Chinese, Japanese, Hebrew, Hindi, Greek, and now there is an actual reason why LT-SPICE does Unicode, and that reason is, well, you can blame it on the Russians. It is in fact their fault. See, I go to Russia every year. Okay, I go to Russia every year because they claim to graduate more engineers than any other country. I don't know if that's true, but I actually will go anywhere people will listen to me. So I end up going to Russia. And I've been everywhere in Russia. I mean, I've been to Novosibirsk, which is against the Mongolia, deep into Siberia. I've been to Ekaterinburg, which is just north of Kazan, and also in Siberia. You know, Rostov-on-Don, southern Russia, near Georgia. You know, I've been everywhere in Russia, and I go there every year. Now, if you know any Russians, you know what their reaction to this talk is going to be. They'll listen to all this, and they'll go, well, that's all very nice. But you understand, we want our schematics in Russian. You get that, don't you? So, now this was an awkward thing for me to entertain because I think of a schematic as something that I will first convert to a netlist, and then I will parse that netlist and store that circuit in data structures, and then execute intermediate code. You know, basically a SPICE simulator is a compiler. That's the technology. If anyone wants to be a software developer, study computer science and compiler theory. That's what you want. Everything else is just vocational. But if you really want to know how to do software, it's how you need to know how to write compilers. And LT-SPICE is a compiler. Now, every single compiler, every single programming language is done with ASCII characters, where the A stands for American, right? I mean, you know, and Latin keywords. And even though I'm a native English speaker, that's not my fault, okay? You know, if you're in Russia programming, doing software development, you're using Latin characters and English keywords. So their request that they would want something in Cyrillic was awkward for me to entertain. But if you think about it very long, as in probably less time that I spent to talk about this, you'll realize they're right. It's not, you know, they should have those schematics. It does every character of every living language, and specifically for the Russians. And I don't think that that's going to do much for you, but does that. Ooh, this is fun. Okay. All right. So you ready for the demo? I mean, it seems like if you go to a software seminar and there somewhere, there ought to be a demo, and you probably shouldn't miss the demo, you know? So let's do the demo. Okay. Now, when you start up LT Spice, it looks like this. This background picture here, that's to let you know that that's not a schematic. Okay, LT Spice 4, the background of the application, the background is schematic with the same color. So that start LT Spice 4 and you try to draft something, nothing would happen. It was not a very pleasant experience. So now it has this pattern here, so you know it's not a schematic. This actual pattern is actually it's called the Antikythera mechanism. It was a analog computer found in the ocean just off the island of Antikythera in Greece. It's about 2,300 years old, this gearwork thing. It's an amazing thing. It kind of shifted what people thought of, you know, technical development. But this gearwork is 2,300 years old from Hellenistic Greece. It was used for referring the Greek lunar calendar to the Egyptian solar calendar. And it kept track of lunar eclipses, and it also kept track of the all-important Olympic Games schedule. That's what it did. All right, now, but you could choose other background patterns there. Anyway, now when you start a schematic here, this is now my blank piece of paper, and I can draft on this schematic. Now, the nature of the demo I'm going to use, I'm going to design a switch mode power supply. I'll implement the switch mode power supply with a controller IC that will control a power MOSFET. This controller IC, that's what's manufactured and sold by Analog Devices. They don't list this as various third-party parts. All right, now the F2 is the symbol browser, and you can open up the symbol browser and click on a symbol. It'll show you a picture of it, it'll give you a description, it's available. And you also can type into this little section here and immediately jump to a symbol. Okay, you know, if I just type the first couple of letters, it will try to jump to it. That's actually the way I use the symbol browser. I never browse through the symbols. I type in the first couple of letters, and that gives me instant random access to every symbol of the record. So that's just the only way I'll use it. Now, the symbol browser can also spell check. The controller IC that I want to use, it'll be the Analog Devices LTC1624. But I can just type in the number 1624 and it spell check that to the LTC1624, and that will be my controller IC. Very good. That controller IC will control a power MOSFET. It's an N-channel MOSFET. I will also need a diode. I need an inductor. I will need some resistors. I need some capacitors. And I also need a voltage source. All right, so now I'm going to make the electrical connections. F3 starts being wire draw mode. All right, so right now I know I am talking to people who have used LT Spice before. And the reason why I know that is by the sound that I'm hearing in this room when I draw these wires. Okay. People who haven't seen LT Spice haven't seen automatic wire cleanup, where I can just draw a wire through a part and it cleans it up, okay? Like here's the ground pin, I'll draw it right through the part and it cleaned it up, you know? People who haven't seen LT Spice before, they haven't seen drafting done that way. And for example, take these three parts. Okay, so I want to connect these all in series, and I don't have to go click, 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 click. You know, I just draw one wire through the part. So when I do that, if they haven't seen LT Spice before and I do that, they go, oh. You know, spiritual experience, you know. And I'm not getting that sound from this room, so I'm pretty confident that you guys have. Look, you know, let's just have it out. Let's see how much expertise we've assembled here at the University of the Philippines for LT Spice and abroad. I want you guys to play too. Do we have anyone here that's a real expert LT Spice user? I mean, do we have anyone here that's so good at LT Spice that they should be the one giving this talk? Remotely? No? It's all right. Sometimes I have one, all right, but not today. All right. It's so totally cool, you have no idea. You don't have to be shy about this. It's all right. Well, how many people here use LT Spice? Raise your hand if you actually use LT Spice. Oh, these are my people. And, yes, I'm back to. So, very good. These are my people. All right. Do we have anyone here that's never used LT Spice? Yes! I have an opportunity for market penetration. That person over there is my best friend today, you know? So, all right. Anyway, let me make some more wire pictures here. And see, finish drawing electrical connections. We've got one more connection to do. All right, there we are. That's my schematic of a switch mode power supply. And to the best of my knowledge, it's correct. I didn't make a mistake on purpose. If there's a mistake in it, it'll show up when I start trying to simulate the thing. But as far as I know, this is a correct schematic of a switch mode power supply. But despite the fact that it is possibly correct, I can't simulate this circuit yet because I haven't said what the component values are. Simulators don't symbolically solve your circuit with equations. They numerically solve it for all the concrete values that you have in all the components. So that means I have to say what these component values are. That means I'm going to edit these components. All right. Now, even if you're an established LT Spice user, let me point out that there are 3 ways you can edit symbols in LT Spice. There's 3 different GUIs you can invoke to do the same thing. So as I edit this, let me call attention to which GUI I am using. All right. First of all, there's these 3 different GUIs. They are first in expert mode. Second, an assisted mode, where the software helps you edit the component. And then there is finally third, the super expert mode. And you use the super expert mode when you're absolutely positively certain that you're more clever than the software. All right, now, so first, expert mode. That's the one you use most of the time. The nature of invoking the expert mode GUI is you point at text, right-click, and type in what text you want. For example, take this resistor here. This is the current sense resistor. It's some number of milliohm that has a fraction of a voltage drop for a full-scale amperage of current through the resistor. Now, to use expert mode, I take the mouse and I point at the letter R. You can see the mouse cursor changes shape from a crosshair, like you'd use in drafting, to a text caret. That text caret is trying to give you tactical feedback that you are pointing at that letter R. Now I right-click and I type in the text I want. I want that to be 33 milliohms. That's expert mode. Point at text, right-click, and type in what you want. Let me enter some more component values using expert mode. Here's the feedback resistor network. This is the output filter capacitor, and I'll use 100 microfarad. This resistor here is the load. It's basically the test vector for my power supply. I'll make that a 3 ohm resistor. Here's the compensation cap. And there we are. Okay, now, this voltage, let me first check this out a little bit. All right, this voltage source here. Now, it turns out that the simulation that I want to do is something I call the startup transient analysis. That is, I want to watch this power supply come up running as I turn it on. I'm a real big fan of doing startup transient analysis. Now, to do a startup transient analysis, to watch the power supply come up running when it's turned on, I have to turn on the power supply during the simulation. And that means that this input voltage source is not a DC value. It is a waveform that starts at 0 at t equals 0, and then some short time later comes up to my input voltage and is that input voltage ever after. Now this converter is going to be a 12 volt to 5 volt buck regulator, so I'm going to effect this input waveform, this 12 volt voltage source, with a piecewise linear source with a single piece in it that starts at 0, and then at 1 microsecond into the simulation will come with the 12 volts. And I entered that with expert mode. I just typed in the syntax that makes that a piecewise linear source with the single piece of the waveform I want. I did that in expert mode, and I could do that in expert mode because I knew the syntax. But that brings us to the second way of editing symbols in LTSpice, assisted mode, where the software helps you compose the syntax so that you, okay. Now, to enter assisted mode, you don't right-click on text. You right-click on the component body. So if I bring the mouse cursor and point at the body of the component, I get this little hand icon that says you're pointing at the symbol. So I point at the symbol and right-click, and that will launch a GUI to help me edit that type of component. You can see this little piecewise linear source here. There's a little spreadsheet editor at t equals 0 at 0 volts. At 1 microsecond, it's 12 volts. That's assisted mode. The assisted mode helps you compose the syntax. And every single different type of electronic component has a different syntax. So there's a different GUI depending on the type of symbol you want. Now take this diode here. When you put a diode in a simulation, you want to use the right diode model so the forward drop is correct and so it has the right capacitance. Now I could edit that diode in expert mode. I could right-click on this letter D and type in the name of a diode in my diode model database, and that would be a correct way of editing the diode. That is correct, but that's clearly ambitious because you have to spell it exactly right, and you have to know what diodes are in the diode model database. So let's not try to type that in. Let's not do that. Let's instead use assisted mode. You right-click on the body of the diode, and that brings up a GUI which initially displays the edit state of the diode. Now there's this button called Pick New Diode, and when I press the Pick New Diode button, the schematic capture program will read the diode model database, parse it into data structures, and give me a list of diodes. So let's do that, and now I can pick a diode off of this list. So what expert mode is doing for you in the case of a diode is that it is promoting the problem of editing this letter D from an essay question to multiple choice. That's what it's doing for you. Now you can actually see the diode model statements here, and these diode models are annotated with selection guide information. And the selection guide information is displayed out here in these individual columns, current rating, voltage rating, and you can sort according to selection guide information by clicking on the column heading. This is going to be a power supply. I'm going to want a high current diode, so I click on the current scale, and I want to find something with that's going to handle some real amps here. Here's a diode. It handles 7 amps. And it is a Schottky diode. So a 7 amp Schottky diode, that sounds like that I'd like to use that, okay? So what's going to happen now, when I double click on this letter D will change to precisely match the name, coincide with the name of the model. That's one thing that will happen. And the other thing that will happen, instead of using the generic or silicon diode symbol, I'll use a Schottky diode symbol. So when I click on that, you can see it's edited the text and it changed the diode. So that's assisted mode for a diode. So the nature of assisted mode is pretty simple. You click on the body of the component and a GUI that comes up that tries to be helpful in composing the syntax for that diode. Similarly for this MOSFET, yeah, I could use expert mode. I could type in the name of a MOSFET model, but that's, I don't know what models are in the database just by looking at the schematic. And actually it turns out it's even more important to use the right MOSFET model for a MOSFET than it is to use the right diode model for a diode. It's even more important, and the reason why it's even more important is because by convention in simulation, the default behavior of a MOSFET is not behavior of a power MOSFET. The default behavior of a MOSFET in circuit simulation is the behavior of a submicroscopic transistor as one would lithograph onto an integrated circuit. And that thing will only switch microamps. It won't switch amps. So if you put a MOSFET in a simulation, you say, oh, I'll just use the default MOSFET because I'm not comfortable with saying what this MOSFET I'll do. I'll just use the default. It'll behave like it's not there because you're only going to be switch microamps. It's a submicroscopic transistor. So we have to say which MOSFET we're going to use. So we right-click on the MOSFET, pick new MOSFET. I know which MOSFETs I have in the lab, so I will pick one that I have in the lab, and I'll just use that MOSFET. So there it is. Okay, so that's assisted mode. The nature of assisted mode is you right-click on the body of a component, and that will launch a GUI that will help you edit that type of component. And there's a different GUI for every single different type of electronic component, even something as simple as this capacitor. Now, this is the output filter capacitor, and I used so-called expert mode to edit the capacitor. I just right-clicked on the letter C, and I said it's 100 microfarad, and I felt that was done. Well, yes, that's one way of editing the component, but I could also have used assisted mode. I could have right-clicked on the body of the capacitor. That would launch a different GUI, and it would give me a place to enter the capacitance. I could have done that should I have felt like I needed that type of help. But the value of assisted mode for a capacitor is that you can add parasitic impedances. You can add a ESR. You can add an internal inductance, a shunt leakage, a parallel capacitance over this whole series RCL circuit. So you can add all of these other parasitic impedances in assisted mode. Now, it turns out that when you're simulating a switch mode power supply, you have to use an appropriate value for the ESR of the output filter capacitor. I mean, it's real important. That output filter capacitor ESR, series resistance, that output filter capacitor ESR qualitatively impacts the operation of the circuit. And by qualitatively impacting the operation of the circuit, what I mean is, if you have the wrong value of ESR in there, the resultant waveforms will look entirely different in an unrelated way. And had you used an appropriate value of ESR, it's that big of a deal. It's like having a component with the wires all screwed up. It's that big of a deal. Now, if you don't know the ESR of an output filter capacitor, that's okay too. There's a button here called Select Capacitor, and you can access a database of capacitors. And let's just pick some god-awful aluminum electrolytic and let that be that. Okay, good. Now, look at, now when I did that, two things happened. Now I'm using the American symbol for a polarized capacitor instead of the American symbol for an unpolarized capacitor. I have to say American symbol because in Europe they use different symbols. Use the American symbols here in the Philippines, or good. We're off to go. All right, great. So you can see it's a polarized capacitor instead of unpolarized, and you can see it's 100 microfarad. Great. But when I right-click on the body of the component, the initial dialog shows the edit state. See, it knows the manufacturer part number, dielectric technology, voltage rating, current rating, ESR. All of this information is annotated on that symbol, but not all of that information is visible on the schematic. That is, I've edited something that is invisible. And the fact that I've edited something that is invisible, that brings us to the third way of editing symbols in LT-Splice, the super expert mode. Now, to enter the super expert mode, instead of right-clicking on text or right-clicking on the component body, you hold down the control key and right-click on the component body, and then you will have a GUI that will display every attribute and every value, and you can see where that invisible information is stored. And you can edit it. You can make it anything you want. You can make any attribute, any text string you want. Okay? And you can choose whether or not it's visible. This column here, VIS period, is an abbreviation for the word visible. And if I check that, this text will now be visible on the schematic. And there it is. Okay? So in super expert mode, you can make any attribute, any text string you want, and you can choose whether or not they're visible. You can completely have your way with the symbol attributes. So, but, really what this means is Super expert mode is a very good way of generating a lot of error messages. It's real good at generating a lot of error messages. So now let me undo these edits. Let me go back to an output filter capacitor that I will simulate as a numerically ideal 100 microfarad reactance with no ESR. That's actually a mistake, but within the context of the demo, I will start with that particular mistake in my schematic. Okay, so at this point, I've edited every component. I have a completely concrete example of a circuit. There's only one more piece of information I have to give the software before I can run the simulation, and that is I have to say what type of simulation I want to run. SPICE allows you to do many different types of simulation. You can do a transient analysis. That's what it's famous for. That's analogous to simulating the waveforms as you would see on an oscilloscope. That's what SPICE is about, is transient analysis. But there's, SPICE will linearize your circuit, expand your circuit as a first-order Taylor series, and drop all but the first-order term and do a linear AC analysis. You could look at, which is useful for filters and looking at things in the frequency domain. See, if you have a linear circuit, you can describe it in the frequency domain. All the frequencies are independent for a linear circuit. Normally, they're not. Normally, it's incorrect to look at a circuit in the frequency domain. Normally, it's just wrong because it's not a linear circuit. But if you have a linear circuit, you can, and the simulator itself will expand all these nonlinearities as a linear circuit, as a Taylor series, and keep only the first-order term. And just, you can do that. So, and there's also noise analysis. It will, after it, instead of doing it, it looks at it as a linear circuit that considers the stochastic noise mechanisms, from Johnson noise and thermal noise and flicker noise. You can decorate components with flicker noise, unknown one-over-f noise sources. There's DC sweeps if you want to curve trace transistors. But anyway, you have to say what kind of simulation you want to do. Now, to do that, you put a simulation command on the netlist. And you put a simulation command, a SPICE directive on the schematic. And in handling these SPICE directives, this is one place where LT SPICE 4 and LT SPICE 17 differ. They look similar, but they actually behave very differently. In LT SPICE 4, it was expected that you would have a one-line SPICE directive on the schematic, and when you right-clicked on that one line, some GUI would launch to help you compose the syntax of that one line. If you wanted to put two SPICE directives on the schematic, it was expected that someplace else on the schematic, you'd have one other line, and you'd put that someplace else on the schematic, you'd right-click on that, and some other GUI would launch to try to help you compose that text. Well, after I added a number of different GUIs for composing single-lined SPICE directives, I realized this was not a very good organization. So instead, LT SPICE 17 will cooperate better with having one block of text, and you can point at a line in it and say, launch the GUI for that line. Okay, so if I want to help composing this line of text, I point at this one line, right-click, and there's a command called Help Me Edit. That's going to help you compose SPICE syntax. These are all the different GUIs for different types of SPICE syntax. I want the analysis command, and then I can use this GUI here for analyzing the analysis command. And as I enter information in this GUI, you can see that the actual SPICE command down here is listed. Okay, every time I edit here, every time I edit something here, it shows what the command, what the resultant syntax looks like. Or I can just type in the syntax directly. And as I type, whatever I type is parsed into the GUI. So what's happening here, there's actually two user interfaces in this GUI acting together. There's a GUI, there's a graphical user interface, and there's a command line interface. And the user input from these two user interfaces is ORed together to the software. Now, the reason why LT SPICE is organized like that is because there is a very wide range of people who need to do SPICE simulations. Some people who need to do SPICE simulations don't know SPICE syntax, and more importantly, they don't want to know SPICE syntax. And that's okay. There's a GUI. You can put the information in your GUI and get on with your life. It's fine. There are, however, also other people who need to do SPICE simulations, who have been doing SPICE simulations for decades. And the last thing that those people want to have to do before running a SPICE simulation is to have to fill out some form. They're really not interested. They want to type in the syntax directly and get on with their lives. I mean, for those people, this is about as clever as a new email client that doesn't require you to type because you have a picture of a QWERTY keyboard and you poke at the keys with your mouse. I mean, it's not what they want. So that's why these two GUIs are there. So anyway, in general, the policy in LT SPICE is this. If you know the SPICE syntax to what you're trying to accomplish, you're welcome to use it. Otherwise, there'll be a GUI to help you compose it. That's the deal. All right, now here, there's my analysis command. And there it is. So now at this point, I'm ready to run the simulation. What happened to my market penetration opportunity? I'm sure he's around here someplace. So anyway, I hope the question that's just burning at the top of your head is, well, how do you run one of these simulations? I hope he's not sitting there wondering, who is this guy? But anyway, that's not even good. All right, when you want to run a simulation in LT SPICE, it's pretty straightforward. What you do is you press the run button. You see this little running man? That's the run button. When you want the simulator to go, you poke the running man. Now the thing is, this is different than you usually find in SPICE simulators. Usually the run button looks like play on a VHS deck. It's a little arrow. Well, 20 years ago, I looked at that little arrow and I said, those decks are doomed. They're not going to survive. So I made a little running man. When you want the simulator to go, you just poke the running man. So anyways, you poke the running man and you run a simulation. Okay, great. Now, for the rest of you who have been using LT SPICE, I want everybody to think back to the very first time they ran a simulation in LT SPICE. You know, how did that really go? You know, you had the schematic and you had to edit it, and depending on what you clicked on or exactly how you clicked on it, a different GUI would launch. Okay, but what are we as engineers? What are we as people? What are we as engineers but people that will do whatever it is necessary? I mean, full stop. That's what we are as engineers. We will do whatever is necessary. That's who we are. You figured it out. You edited that schematic. Great. And then you had to find the run button. But again, who are we as engineers but people that will do whatever it takes? You found that run button. And then you pushed the running man, and what happened? You got an error message. And then you read that error message and you says, that's right, and you fixed that problem. And then you poke the running man, and now there's a different error message. And you looked at it and says, that's true too, and you fixed that problem. And then you poke the running man, and you got another error message. You looked at that and it says, it's got a point, you know, whatever. But who are we as engineers but people that will do whatever it takes? Eventually, you poke the running man, the simulation runs, you have a waveform window, but there's no data plotted. Now at that point, I think it's very normal to wonder whether you should say thank you or not. So that's not for my new market penetration opportunity, so they can avoid that awkward moment. Let me show you how to plot data. But there'll be enough new material, even if you're an established LT SPICE user, there'll be some new stuff here. Now the first thing for plotting data is just keep in mind, you can plot anything that you can point at. If you can point to it on the schematic, you can plot it. For example, take this node here. If I take the mouse cursor and point at this wire, it turns into a little red voltage probe. That is trying to give you tactical feedback that you are pointing at a voltage that you could plot. Left mouse click, disco, there it is. Point at another wire, I get the voltage probe, there it is, add that one. Another probe. So every time you click on a trace, it will add a waveform to it. Now, if you want to plot one trace by itself, double click on the wire. So if I go click, click, there it is. Click, click, every time you double click, it will delete everything you plotted up to that point and show me that one trace auto-scaled in isolation. But you can also point at currents. If I take the mouse and point at the inductor, you see the mouse cursor turns from a cross-drafting crosshair to something that is trying to look like a little clamp-on amp meter icon. That means I'm pointing at that current. There's the inductor current, current sense resistor current, output filter capacitor ripple current, and so on. Now, if I want to plot the transistor current, the current through the MOSFET, if I try to point at the MOSFET, if you take the mouse and point at the MOSFET, I don't get the little clamp-on ammeter icon. I just get this little hand that says, you're pointing at the MOSFET, and it doesn't seem helpful. Well, because the MOSFET has 3 terminals, you have to see which terminal current you're interested in. So if I point at the drain, I get the clamp-on ammeter icon, and that's giving me tactical feedback. I'm pointing at the drain current. See, it's listed ID of M1. Okay, now if I point at the source, I also get the clamp-on ammeter icon, and when I clap that, it looks like the same current, but the opposite sign. Pin current sign convention is positive into the pin. That's why those look like similar currents, but opposite signs. Similarly for the gate current. There's the gate current. You can plot any pin current. I can plot the feedback pin current. I can plot anything to point at. But actually, let's think about this for a little bit. I'm plotting the current into the feedback pin. But in a circuit like this, the job of the feedback pin is to sense the voltage on the output of the voltage divider without changing that voltage by drawing current from it. Yet here I am plotting the current into the feedback pin. Well, it's all good. It's nanoamps, so it's a tiny current. And most of that current is actually just flowing into the capacitance of the pin. So there is no. So you can plot anything that you can point at. Now, not only can you plot anything that you can point at, you can plot anything that you can type on the keyboard. Let me start by editing this expression. Instead of plotting this pin current, let me plot this pin current squared. If I can type it, I can plot it. Now, one thing I'd like to point out is that the symbol, the exponentiation in LT-Spice is done with star star. It is not done with a caret. A caret means XOR. It's more uniform with software development than core engineering tools. Star star for exponentiation, and XOR is the caret is exclusive OR. All right, great. So you can plot anything you can type. Anything you can type. If you want to plot 5, you can plot 5. Anything you can type, you can plot. If you want to plot, say, 2 times pi times the square root of time, it's all good. Anything you can type, you can plot. Now notice that LT-Spice keeps track of the physical units of the data that it plots. See, it does a dimensional analysis of this expression, and it labels the units accordingly. See, 2 and pi have no physical units, but time has the units of seconds, so the square root of seconds would be root seconds. That's why that's labeled in root seconds. Now, the reason why that's useful is that, say you're plotting data with different physical units. See, right here I have something with root seconds, a couple of voltages, and a couple of currents. There's 5 traces of 3 different types of physical units. So there's 3 different vertical axes: root seconds, voltage, and I can't see the amps. So there's the amp scale. So yeah, root seconds, volts, and currents. That's why there's 3 vertical axes. Now the motivation for that strategy is twofold. It plots. It's a fairly good strategy to plot data of different physical units on different vertical axes, because if you have different physical units, it's very common for you to have wildly different numerical ranges, so you can't see it on the same plot. For example, say I don't plot this voltage, but this voltage cubed. Okay. Well, so now it has to add this voltage cube scale. Here's a voltage cube scale and a voltage scale, and you notice they have radically different numerical range, 140 compared to 1.3. So you wouldn't be able to auto-resonate, different, that's one reason. It's a strategy so you can see all of your data. And also, there is no comparison of a volt to a volt cubed. They're just different things. Now you can force them to be in the same axis by changing the units. Say instead of plotting this volt cubed, say divided by 1 volt, divide by 1 volt. Now I just have a volt scale. But you can't see the, let me delete the other traces. So you can see this one, but you can't see so you have, these all have the units of volts, but you can't see the one that's actually started out of volts. I could multiply by, a factor so you could see them all, but that's basically where it comes from. So, all right. So you can plot anything you can point at, you can plot anything you can type. Great. But there's more. Not only can you plot anything that you can point at or anything that you can type, some things that you can type are so useful. Some expressions of data that you can type are so useful, you don't have to type them. You can compose expressions of waveform data with mouse syntax. Let me give you some examples. Say I want to know the voltage across this current sense resistor. Yes, I can plot one single-ended voltage or the other single-ended voltage. If I want to know the voltage across the resistor, I could type in V, open parenthesis, node name, comma, node name, close parenthesis, and that would be a correct way of plotting that voltage difference. And that's fine if you don't mind typing and you know the names of the nodes. But you can just drag the mouse between the two nodes. See, if I take this mouse and point at this wire, I get a red voltage probe. Now I'm going to drag. Drag means holding down the mouse button while moving the mouse. That's dragging. And now this is my mouse cursor. This is supposed to look like a grayed out ground clip, a disabled ground clip. If I bring this mouse cursor to a node electrically distinct from where I have left this red probe, the mouse cursor turns black. And that is trying to give you tactical feedback that you're pointing at a voltage difference. That's the voltage across that resistor. Now, given the voltage across that resistor, I could further edit that expression to be the voltage across it times the current through it to plot the dissipation in the resistor, but that's another expression type that you can compose with mouse syntax. See, if I point at the resistor, I get the clamp-on ammeter icon. I am pointing at the current in that resistor. But now if I hold down the Alt key, it turns into a thermometer icon. I'm now pointing at the dissipation in that resistor. Okay? And the algorithm that computes dissipation is completely general. If I take this mouse and point at the IC, I get the little hand that says I'm pointing at the IC. Sure, I can point at a pin and plot a pin current, but if I point at the IC and hold down the Alt key, it turns into a thermometer icon. That is now plotting the dissipation in that IC. And that expression here, that big long expression, is simply summing the integrated pointing vector over all ports of the IC. And it's easy for LT-Spice to compose that expression for you because it knows the names of all the voltages and currents. So there's one more expression type you can compose with mouse syntax, and that is, if you will, the current in a wire. See, when I point at this wire, I get the red voltage probe. I am pointing at the voltage on that wire. But if I hold down the Alt key, it turns into a current probe. Okay, so now I'm pointing at the current in the wire. So I'm pointing at the voltage, I'm pointing at the current. Pointing at the voltage. I actually love this. This is, I don't get much out of life, but this is all I get is this thing right here. So I'm pointing at the current wire. And again, that's another text manipulation scheme because the wire is not a wire in the sense that it has any impedance. It's just that when you draw a line on the schematic, the meaning of that line is that both ends have the same electrical node. That's the one and only thing it means. It knows the names of all of these currents and how they would sum up into a line on the wire, and that's what it's computing for you. Okay, there's one more thing I want to show you about cross-probing, and that is after you get done with a lot of data, you might look at this and say, oh, well, which one was N002? Well, that's okay. Point at N002, hold down the Alt key, and it will highlight it in the screen, so you can cross-probe in both directions. You know, if I want to know which trace was N001, it will remind you of that by highlighting, so there it is. Okay. Now, you can also put node labels on things. Let me label the output. Here's the output. Here's the input. All right, great. So now this output will now be, this is now labeled out. And I want to talk about this output. Now, I realize that when you get done with your university studies, you're probably not anticipating that when you get your first job in industry that you spend your day looking at the waveform on the output of a power supply. Right? I mean, that's not what you're looking forward to. I get that. That's exactly what I do for a living. I'm all about the waveform on the output of a power supply. That's what I do for a living. So I'm going to ask you to think along with me when I look at this waveform on the output of a power supply. Let's read this waveform and see what we can infer from it. First of all, this is during startup. So at t equals 0, it's turned off. And you'd expect the output to be 0 from inspection of the problem, you expect the output to be 0, and it is, so that's good. Now, here's a big deal. When you turn the power supply on, what you want to see is the output come up to the right output voltage. That's a big deal. When you make a switch mode power supply, anything can go wrong, and that might not happen. For example, I might have forgotten to edit this as to be a power MOSFET. If it doesn't pass any current, this output would just stay down there. It would never come up. Or it might, if I put one of these wires in the wrong place, the circuit won't switch at all, so that won't work. In fact, it might not start up for a subtle reason that would be missed even in a correct static analysis of the switch mode power supply. And here's what I mean. Say you implement this power supply with a controller IC that implements current foldback as a strategy for self-preservation in the event that the output is accidentally shorted to ground. Many power supplies will not operate at current limit into a short circuit on the output, because you have this huge voltage difference between input and output, and if you put all that current through it, all that current times that voltage difference is a lot of power, and you could blow something up inside of the power supply. Many power supplies implement current foldback as a strategy in the interest of self-preservation in the event of an accidental fault short circuit to ground. But if your load actually needs a lot of current at low output voltage, it will just sit there latched off in current foldback. It'll never start up. And a resistor is fairly aggressive. If you're at a third the rail voltage, it needs a third of the current, which is a lot. So that's a fair bit of current. It might, it's fairly hard to start up into a resistor as these things go if you have current foldback. And that would be something that would be missed even in correct static analysis of your power supply. But basically, it's like this. If I see the output, if I do a startup transient analysis and I can see this power supply can start up into the load, I'm a pretty happy camper. And I figure I can fix any other problem that I find objectionable in this waveform. Now, the next thing, when I'm critiquing the startup waveform of switch mode power supply, is I look for overshoot. I don't want this voltage to, this converter I made is 12 volt to 5 volt buck. I don't want the design of the power supply or its loop compensation to be such that the output first goes all the way to 12 volts, over voltages the load 2x, destroys it, fills the room with smoke, and then some milliseconds later is a good little power supply with an S-step 5 volt rail on it. I don't want it to behave like that. Okay? And I don't see overshoot, so I'm happy with that. And then I want to see a DC level. We'll talk about that DC level in a minute. But basically, the startup, what the startup transient analysis does for you in the case of a power supply, it tells you whether or not it will start up into the load, whether or not it will destroy the load when it starts up, and whether or not it will power it with a DC level. So the startup transient analysis is the only simulation of a switch mode power supply that you can do that will tell you whether or not your design qualitatively functions at all correctly or not. All right? Now, that's why I do it. That's why we actually startup transient analysis. Now let's talk about the DC level. Is that the waveform of DC? Well, that's debatable, if that's a DC waveform or not. I mean, if you put a multimeter on it, it'll read 5 volts. At least any multimeter that I've seen manufactured in the last 20 years, they have enough input filtering on them that they will not allow our ripple to alias back to DC and give you screwy random numbers for a readout. So any multimeter in the last 20 years, it'll read 12 volts. And yeah, it's got a lot of ripple. And if you try to quantitate academically whether that's AC or DC, whether or not with, with Fourier analysis, yeah, the biggest component's DC, okay? So in that sense, it's DC. If you connect your load up to it, your load will probably function. But there's all this ripple, and you probably don't want that amount of ripple on your DC voltage. So to reduce that ripple, what you first need to do is find out what is causing the ripple. Basically, well, it's like this. When you make a switch mode power supply, you are going to have ripple on your output. It's unavoidable. It cannot be zero. Okay? So if you want to reduce it, you need to find out whether or not that is switching ripple. If that is ripple due to these two output reactances, this inductor and this capacitor, if that ripple is just these two components not filtering that waveform to DC, but that's the situation, then what you're going to have to do is you're going to have to buy a better output filter capacitor. There's not that much you can do with the inductor. That's the only thing you can do. So let's compare the frequency, let's see whether or not this is switching ripple. And to see whether or not it's switching ripple, you find out if it's at the switching frequency. So the fastest way of exposing the switching frequency of a switchable power supply is to look at the inductor current. Okay, because the inductor current ramps up and down at the switching frequency. And you see it ramps up, down, up, down, up, down. That's a much higher frequency than this output voltage ripple. So this output voltage ripple is not switching ripple. What this means is this power supply is oscillating. That's what it means. Now this is actually, this feedback loop is oscillating. Now this is actually a really, really, really interesting situation, because if you were to go build this circuit in the lab, it would be perfectly stable. It would not oscillate in the lab. And this is many people's favorite topic, the difference between simulated and measured waveforms. And you'll find in your life many spirited discussions about the difference between simulated and measured waveforms. People pay other people to have these discussions. It'll be a fun part of your career. But you should be aware that much of the discussions of the difference between simulated and measured waveforms is motivated by an agenda that is not in your interest. For example, say you got some old guy like me. I have been designing circuits since the 1970s, before circuit simulation. Okay. Now, in 80s and 90s and noughts, circuit simulation becomes popular. Well, that's like terrible. I mean, I was there then. I felt the pain. I bled, and I can design these circuits. Now with these simulators, somebody fresh out of university might design a better circuit than I can. They haven't bled. That's the horror. So now if this old guy can say, the simulated and measured waveforms don't agree, then everything's okay for him again. Because obviously you can't use simulation as part of your design flow, because it doesn't give you results that you can rely on. So you still need me and all that dried blood on my corpse that I have left. You still okay. So that is an agenda that is not in your interest. Now let me tell you that there is a trick to getting simulated and measured waveforms to agree. There's actually a trick to do it. The trick is you have to build what you simulated. That's it. You can write a simulator, and it's incredibly robust technology. I mean, it's compiler technology. A compiler, what is a compiler? It takes some program, some source code you never saw before, parses it, puts it in data structures, generates some intermediate code, and executes it. Well, that's, there's a way of doing that, and it's just incredibly robust. It's one of the most beautiful parts of the time we live in, is compiler theory and how to write this thing. And it really is, it's what's changed our lives more than anything else. Compiler theory, it's amazing. And it's incredibly robust. If you write a program in C and you compile the next run the program and you don't get the wrong results, it's not the fault of the compiler. Okay? That's just the way that technology is. So circuit simulation is all F equals MA. You can't push a rope, you can't pull water. You can write a simulator, okay, and it will work, and it's incredibly robust. What you cannot do, what is off of the table, is you cannot rearrange a few surface mount components and violate Kirchhoff's law. See, that's what you can't do. If you build what you simulated, they will agree. That is how that works. It really isn't any more complicated than that. However, you can't build that circuit. It's impossible, because you would use a real capacitor, and a real capacitor would have ESR. That ESR would put a zero in the loop response, and that will make it stable. Now let's talk about capacitor ESRs. All right, it's particularly aluminum electrolytic. Say you have some aluminum electrolytic capacitor here. The ESR of an aluminum electrolytic capacitor, what do we put in this value here for ESR, equivalent series resistance? Well, the ESR of an aluminum electrolytic capacitor is measured in ohm. It might be an ohm, or 2 ohms, or half an ohm. It's so much ohm. However, in the last, in the last 15 years or more, there are now very carefully procured. You can get exotically good aluminum electrolytic capacitors with very low ESRs. You can get an aluminum electrolytic capacitor with as little as 20 milliohms. You can buy them, but that is a carefully procured aluminum electrolytic capacitor. That is not aluminum electrolytic capacitor in your grandmother's radio. Okay, so if you use that amount of ESR in there, you'll see this power supply is perfectly stable. And that was the mode of operation of every switch mode power supply up until 20 years ago. The output filter capacitor probably made the feedback loop stable, or at a very minimum, it increases phase margin. So you see some advantages to that ESR. You know, it makes the feedback loop stable, or at a very minimum, increases its phase margin. And since you increase the phase margin, the thing will ring less under a step load response. So the power supply actually regulates voltage better because of the output filter capacitor ESR. Again, in the frequency domain, the way to view that is the ESR puts a zero in the loop response, increases the phase margin. Under a transient load response, you will have less ringing as the feedback loop settles in. That's the frequency domain viewpoint of that. Now I'm going to explain the time domain description of the mechanism, because I like understanding both if possible, both frequency and time domain. In the time domain, if there is an abrupt change in load current, that abrupt change in current will flow through this capacitor. It's not going to go through a 35 kilo ohm resistor. It's not going to go through the inductor, because that's exactly what inductors prevent. So the abrupt change of current here comes from that capacitor. If the current flows through the capacitor, it flows through the ESR, and if there's an instantaneous change in load current, there's an instantaneous change in that voltage, and that voltage goes straight into the error amplifier, and the error amplifier immediately starts correcting the point of operation of the feedback loop. That's if you have ESR. If you do not have ESR, and there's an abrupt change in this load current, well, the abrupt change of current, that current flows through this capacitor, and there's no change in voltage across the capacitor. You have to draw current for a while to change the voltage across the capacitor. And that means the error amplifier only later can start correcting the feedback, the operating point of the feedback loop, and it will overcorrect and undercorrect, and it'll ring in and eventually hopefully find regulation. That's the time domain viewpoint of what's happening. I like to understand both if possible. It's always good to understand more. Okay. So that's the advantages of the DSR. Now the ESR has some disadvantages. Basically, because as a series impedance, it increases the impedance of this output filter capacitor, so it doesn't filter as well. You have more, the amplitude of this ripple increases with ESR. And in fact, usually the normal, what happens is this inductor ripple current is read out to a voltage by the ESR of this output filter capacitor. So the amplitude here, it's read out to a voltage. You put current through a resistor, it reads it out to a voltage. There's a phrase I use a lot, read out a current to a voltage with a resistance. I'll use it a lot today. Okay, so the amplitude here, this amplitude is proportional to the ESR of the output filter capacitor. This amplitude is not inversely proportional to the output filter capacitance. The actual amplitude of ripple you have is due to a value that isn't visible in the schematic. That's the normal mode of operation of a switch mode power supply. And so that's one disadvantage. You have the EMI performance of the switcher is not as good because of the ESR, but there's other disadvantages of that ESR. For one, since you have the entire inductor ripple current flowing through that ESR, and that ESR is a real impedance, current through a real impedance is dissipating power. So you've lost, the power supply is not as efficient because of the ESR and the output filter capacitor. Now, I'm not telling you because that's some entertaining, fine little academic detail, okay? That is a huge impact on the efficiency of your switch mode power supply. Today, it's often the biggest loss in your switcher is the ESR, the output filter capacitor. Now, see, the thing is, today, it is easier to buy a 1 milliohm transistor that is to buy a 1 milliohm capacitor. This particular switcher uses it's not synchronous rectifier, so it's not for this particular case. But most of the time, the output filter capacitor is a dominant loss in your switcher. Okay, so you've lost efficiency. There's another disadvantage of the ESR, the output filter capacitor, because you've lost efficiency, you're dissipating heat. That heat is dissipated in the aluminum electrolytic capacitor, and that shortens its life. Okay, now clearly that can be a disaster, but you know that this is a manageable problem. You know that because switch-mode power supplies are designed with aluminum electrolytic output filter capacitors with alarming regularity and success. You can do this. People do this. You can do this. This is at managing this problem. That's why electrical engineers get paid so much money. That's why they get paid more than taxi drivers. You will probably be the final technical authority for the ESR in your output filter capacitors and any power supply you design for a company you work for. And you'll have to do it. That's okay. Now, LT Spice can help you with that because you can simulate how much ESR you need, how much you can tolerate, and there's a database of the capacitors in there. You can put the peg in the slot and get on. You know, it'll all. You can do that. Okay. Now, in fact, not only because it's a general circuit simulator, not only you can actually try circuit design techniques for dealing with AEs. You can put capacitors in parallel, different capacitors in parallel. You can put capacitors in parallel with entirely different dielectrics to make a cocktail of dielectrics that gives you an overall performance as you want. For example, let's try putting some ceramic capacitor in parallel with the aluminum electrolytic. Now, ceramic capacitors have ESR also, but I'm going to ignore it for this because it's a little bit more fun just to ignore it. You consider the worst case for a stability point of view would be having no ESR on the ceramic capacitor, and I'll just do that. Anyway, so the idea is here, this will be a ceramic capacitor. You'll have a very low ESR that I will treat as no ESR, and its job will be it will smooth out these sharp corners. Okay, so I'll improve the EMI performance of the switcher. And but since I'm doing this, I'm going to take this approach immediately to the logical extreme. I'm going to use a huge ceramic capacitor in parallel with aluminum electrolytic because I don't want to just improve the EMI performance. I actually want the inductor ripple current to flow through the ceramic capacitor so it doesn't flow through the ESR of the aluminum electrolytic capacitor, so I get my efficiency back. By huge, I'm not joking. I'm going to use 50 microfarads. Take that. So the idea is I'm going to I'll get my efficiency back and I'll improve the ESR, but I will leave the aluminum electrolytic in the circuit because at the much lower feedback loop crossover frequency, the ESR of the aluminum electrolytic capacitor will still impact the impedance of this node and I will still have my zero. So that's the idea. I get my efficiency, and I'll improve the EMI, and I keep my stability. You can do that. And this would be a viable enough thing to do. However, the only problem with this is that if your boss looks at this, his reaction is going to be like this. He says, okay, if you want to use a ceramic capacitor, that's okay. They're actually cost about the same as aluminum electrolytic. So I'm all right if you want to do that, but you know, isn't the job of this output filter capacitor to store charge so that you have a step-low response that the slower feedback loop can't take care of? You know, you gobble up you prevent the voltage from changing a step-low response with its bulk capacitance. You already have enough bulk capacitance there. Why don't you just get rid of the aluminum electrolytic capacitor? Because, you know, frankly, it looks like it's going to rattle off of the board. You know, I just get rid of it. Use these, you know, no moving part capacitors. Let's just do that. You say, oh, okay, yeah, boss, it's good. We'll get rid of this. We use all ceramic capacitance. That'll make it as quiet as possible, as efficient as possible. Now the power supply is perfect, you know, except for the fact it doesn't work as an oscillator. But other than that, it's perfect. Well, LT Spice can help you with this also, because in a current mode controller, there are two capacitors that implement the loop response. One is the output filter capacitor. That's the dominant pole. Output filter capacitor is typically the dominant pole of the converter. And the other is this compensation capacitor. This compensation capacitor reads out the current from the air amplifier to a voltage, and its value changes the frequency response of the air amplifier. Let's use a bigger compensation cap. You know, let's comp it down. Okay, looks like that might work. But you want to be careful in this, because before you go run to this thing, before you go run to production with this circuit and go start making these things by the thousand, you need to like really search your soul and ask yourself in your heart of hearts, is that the waveform of a stable circuit? Now the answer to the question of whether or not that's the waveform of a stable circuit depends on who is asking the question. Okay, now here on this campus, I imagine that if your professor puts this waveform on your exam and asks you, is that the behavior of a stable circuit? I'm guessing that there's only one answer that'll earn you full credit on that exam. And that is to say that since this ringing is decaying exponentially with time, the circuit has phase margin. So low, the circuit is stable. I'm guessing that's the answer you're going to have to say in the exam to get full credit. Okay? Now, in a commercial environment, that's the wrong answer. Okay? This, I've only done one simulation, and yeah, it just barely is stable. But I mean, if I were to make 1,000 units, they might not, sometimes it might exponentially increase with time. And even if that didn't happen, not one single unit you build would have a good transient response. Everyone would ring like a maniac, like a step-level response. So it's like this. If you make this circuit and sell it to somebody, you're a bad boy, okay? Okay. But again, many switch-load power supplies have a schematic that look this. This is a manageable problem. Many switch-load power supplies will have a schematic that look exactly like this up to these two capacitance values. And you can use LT-Spice to schedule these two capacitance values to trade between loop crossover frequency and stability in a manner appropriate to the commercial context that this power supply is going to be used in. You can do that. Or you could have an epiphany. Now, I don't know if you're familiar with the word epiphany. Epiphany is actually of Greek origin, but this is what I mean by epiphany. An epiphany is like when you look up at the sky and the clouds separate and a bolt of lightning comes straight out of the sky, hits you right between the eyes, flows through your body, fuses your ankles to the earth, and you see everything clearly for the first time. That's an epiphany. And the particular item of epiphanence that I am looking for here is called a feed-forward capacitor. A feed-forward capacitor is a capacitance connected between the output and the feedback pin. We put a it's a low-value capacitor. It affects an RC differentiator against the impedance of the voltage divider, and its job is to advance the phase of frequencies around crossover. And that's what I'm looking for. So this is a feedback loop that's got everything going on. It has a high crossover frequency, it's critically damped, it's got everything except the feedback loop has no personality whatsoever. If it's sitting in regulation and something kicks it, all it does is come back to regulation with no overshoot. So this is the sort of circuit that works when it's made wrong, continues to work after it's broken. It's basically what I'm looking for. Now, let me just point out, are we having lunchtime yet? We can have lunch anytime on your cue. Ah, yes. This man is so patient. He's like it's like I'm going to contemplate what a patient person this is. This is like, okay. I will just continue a couple more minutes and then we shall enjoy our lunch. All right. Now, let me just point out, I did a really amazing thing with that feed-forward cap. Yes, I have this, basically now a perfect circuit. But what I just did was I optimized the feedback loop from the startup transient analysis. That's a new thing. This is actually what I'm known for. Okay, if people get reputations for being ornery or cranky or whatever, I'm known for doing the feedback loop from the startup transient analysis. Okay, and I actually tell people it's the best way of doing it. and here's why. During the startup transient analysis, this output filter capacitor looks like a short circuit to ground. So during the startup transient analysis, the power supply goes from working into a short circuit to into regulation. That's the biggest step load response you can give it. It's a full-scale step load response, and I have a perfect response on full step, and I will never improve on that with doing frequency domain Bode analysis of an idealized linear circuit of this thing. There is no better way of there's no better way of optimizing this circuit. I'm the only person that says this. So this is sort of like where I kind of, I hope there's no professors listening because they don't like this talk. Okay, but anyway, yeah. So it's an interesting thing. I just optimized the feedback loop from the startup transient analysis, and that's actually the best way of doing it. After lunch, I'll put that in a theoretical basis to basically prove that the best way of doing the feedback loop of the current mode buck is in the time domain. You actually can't accomplish what you need to do in the frequency domain. The information you're looking for isn't there. And that's why I'm going to use these droppers. But I do want to, before we go there, I want to show how to properly optimize this feedback loop. I just put it in a value, and then a miracle happened, and everything worked right. But let's show how I get this 330 picofarad. Basically, I just try different values until I find the one that works best. But I could do that in a very organized way. Instead of putting a concrete value, I'll just put in an expression in curly braces. I'm going to call it foo. Foo is not a keyword, just some letters I typed in. And I'm going to step the value of foo. Now this syntax here, dot step, it's something of an industry standard syntax. I just typed it in expert mode. There's a GUI that'll help you compose it. But what this is going to do now is going to run the simulation once for each value of foo through this list of 0, 100, and 200p. And foo is the value of that capacitor, which I put inside of curly braces. And then when I run the simulation, I'm going to run it 6 times, once for each value of foo. And I'll look at the value of the step load response for different values of foo. And finding the value of feed-forward cap is just a matter of multiple choice. You pick the waveform you like the best. This is the waveform I like the best. Now, if we want to read out the value of foo for that waveform, I use something called the attached cursor. To attach a cursor to waveform data, you point at the plot label of the quantity to which you wish to attach the cursor, left mouse click, and now I have this attached cursor. These attached cursors, people like them because it reminds them of laboratory instrumentation with little tiny CRTs you can slide a current read up. If you actually have a computer, very rarely is an attached cursor the best way of doing anything. But you know, it has them because people like them. And here's this little readout screen, and people like to slide these around. You can have fun with these. But I actually have no interest in that data. I just want to use the cursor attached to the waveform data so I can point at different waveforms. Now, when you initially attach this waveform of the attached cursor, it's attached to the first simulation. And the keyboard up-down arrow keys makes the cursor hop from simulation to simulation. So if I press up arrow, it will go to the next simulation, which is lower on the screen. Up arrow again. Now I'm pointing at my favorite waveform. This is, see, it's just slightly underdamped. So I want to know the value of foo that was used for that. So to find the value of foo, I take the mouse cursor to point at the attached cursor. Now the mouse cursor is pointing at the attached cursor, and I go right-click. It says foo was 300p, and I just use the standard value above the value that was just slightly underdamped. And that's how then is a full rigorous optimization of the feedback loop from the startup transient analysis. We're almost ready for lunch. That's the way to optimize the feedback loop. However, it still doesn't tell you it still doesn't tell you how much the output voltage changes under a certain step load response. That's how to optimize it. This is as good as this basic supply can do, but at least as far as the value of feed-forward cap I've used. But it doesn't tell me under a step load response whether or not the error in voltage on the step load is tolerable or not. See, what can happen? This is not the normal situation. But it can happen that a person who asks for a switchboard power supply knows what the power supply should do. That's very highly unusual. Most people want a power supply, they just want a power supply and they don't know what it should do. Okay, but it can happen that they know what it ought to do. And where that happens is when the power supply is powering massive amounts of digital logic, like the core logic of a CPU or something. See, the guy who makes the CPU, he has a spec he has to meet. He says, okay, I'm going to rapidly change the clock frequency of the CPU, and I'm going to, when I rapidly change the clock frequency, it's going to pump a radically different amount of charge to the CPU. It's going to be drawn from, instead of 50 amps, it's going to draw half an amp. And when it does that, I can't have the CPU core power have more than so many millivolts excursion from what it's supposed to have, because if it has too many millivolt excursion, then I won't execute the logic correctly. The flops won't give me always the correct output data. So that's when you have the situation where under step-level response, the voltage has to be within a certain error. That's not usually the case. Usually a person wants a power supply, he doesn't know what he wants. He just wants, he wants it to fit in a certain size, he wants this voltage, and that's all you get. Okay? But anyway, so for that, you need to do a step-level response. And there's lots of ways of doing step-level response in LT-SPICE. You can use currents with a pulse function. I'm going to use a voltage-controlled switch because it might have a little bit of, it's a bit pedantic in the way it shows a few more techniques here, but it is also conceptually more similar to what you do in the lab. And his writer model for the switch. And now you can see the, that's the load current. That's the output voltage. And you can see the thing is critically damped on the infinitesimal change. You can see what the excursion is. You can measure whether or not the performance is within within your specification for step-level response or not. Okay, we can do lunch now.